like that. I'm kind of approaching this as a practitioner. I use standard ML for most of my research hacking, and I really like modules and the type theory that underlies that. So I'm hoping to try to kind of spread the word about them and tell you a little bit about what I know about what that's all about. So the way that I'm going to go through these ideas is just first by starting out with some kind of high-level, waxing philosophical ideas about what we actually mean when we talk about modularity. Then I'll go through the bulk of the talk explaining how standard ML implements a lot of these ideas and how those come across in the type system there. And then I'll spend a little bit of time talking about the type theory and some of the subtleties of that. And then I'll go into some of the research that's been going on since the implementation of the various ML family. I will try to pause for questions kind of in the middle, like after the first couple of sections. And if we could stick to just like clarification questions until then, that'd be awesome. All right. Okay. So modularity is a pretty fuzzy word, and I'm going to start by kind of explaining it in terms of a few other fuzzy words. But in general, as software engineers, we kind of know that like modularity is a thing we want. We want to be able to work on one part of a system without having to know everything about all of the other parts of the system. We want to be able to reason about any of the code that we're using or anyone that might use our code by thinking of those things as kind of black boxes and not having to know exactly how they're implemented. And the primary mechanism for doing this is abstraction, where we kind of give a loose sketch or a specification, usually through types, of what the code that we're writing is actually supposed to offer to some client of that code. It doesn't reveal things about its implementation. And then as an effect of that abstraction, hopefully we get some notion of composability. We have, once we've blurred away all of the implementation details, then we have these components that we can fit together really nicely and know that if we go in and we make some subtle changes to our code and someone is using our code, we're not going to break everything. Okay. So how do we get this in a programming language? All of the ideas that are put into use in the ML family are kind of found, you can kind of find the seeds of these ideas in this one really famous paper from John Reynolds in 1983, where his central claim is that type structure is a discipline for enforcing levels of abstraction. So yes, we are going to do this with types. I'll start by talking about contrasting with something you're all very familiar with, which is the idea of inductively defined data types. So one way that we can say, here's a programmer-defined type in a program, is to declare a data type and say, here are the ways you can build it. You can either build a list with a nil or with a cons and then some other stuff, right? So by contrast, what we're going to call an abstract data type is more accurately described as being defined by how you use one. So let me dive in right away with a concrete example, and don't worry if the syntax is a little unfamiliar. I'll walk through this slowly. So this is a signature in standard ML, which is an abstract data type that can have one or several implementations. The way that we define this new type is does this laser work? Can everyone see the laser? Yeah, okay. So the way we define, no, the laser is being finicky. Okay. The way we define this new type is by declaring it as a variable, not giving a definition to the type. And then we say, what are the operations that we want to have on that type? Well, we want a way of getting an empty one. And then, if this is a stack, then we want some kind of push operation where we can give it some data alpha and get a new alpha stack with that data pushed on it. And we want a way to pop something off a stack, which, as long as the stack is not empty, should give us back some data and the new stack. Okay, so in general, the syntax for an abstract data type or a signature is in ML, you have a signature declared by convention, some kind of all caps identifier, and then you have some declarations which can contain new type variables and some value specifications that refer to those type variables, as well as whatever else you can refer to. Okay. And in general, an implementation of such a thing is called a structure, which is just ML's word for a module, which gives definitions to all of those abstract type declarations. So you have declarations over here, you have definitions over here, and somehow these definitions need to match the declarations. So let's look at a concrete implementation of our stack type. So we'll choose for just a pretty simple example to implement this stack as a list. So in our structure, we give a concrete definition of the alpha stack type as alpha list. Then our empty value has to match that concrete type that we gave, and we'll give it the empty list. Push is just cons, and for pop, we'll do sort of the obvious thing, right? Okay, and then once you have this structure defining some abstract type, you can project out of it and use the values in some you can use this dot notation, which I'm calling projection, to refer to the components of the concrete module. Now, I said that the definitions in the structure need to match the declarations in the signature. What exactly does that mean? Okay, so there's some abstract type, little t, and you're going to give some implementation to that as tau. And if you haven't caught on so far, the convention I'm using in terms of color right now is blue things for abstract typey stuff and like burnt orange for concrete data-y stuff. Okay, so if you implement type t as tau, then anything that's declared in the signature to have some type sigma that refers to that type variable t must, in the implementation, have that same type sigma with tau substituted for t. So, and that's a bit of an approximation here. So it could also be a more general type. So if there's something that says, you have to have an int to int function and you provide, for all alpha, alpha to alpha, then that's okay too. You can also implement more values in your concrete implementation than the signature specifies. So it's kind of got a record subtyping property happening here as well, where you can you just have to provide at least the definition specified in the signature. And the important thing to notice about the relationship between signatures and structures is that it's many to many. So in particular, you can have many signatures to one structure via this kind of subtyping relationship. So for example, this list stack implementation that I was talking about matches the stack signature, but it also matches a more minimal signature where, say, you only, where you only say that there's an empty and a push, and you even specifically refer to alpha list as your type rather than having some concrete type, rather than having an abstract type that's being instantiated. You can also have many structures to one signature, and this is kind of crucial to this idea of having an abstraction where you can have multiple implementations. So let's extend our example to see where that might come across as something useful. So say we want to be able to refer to the size of any stack. We can look at our list stack thing and say, okay, well, the obvious thing is just to use list.length here. But suppose our code is going to refer to the size of the stack a lot, and you don't always want to do this linear query for what you could do in constant time. So we're going to have a new concrete instantiation of the type alpha stack as a pair of a list and an int. And then in all of these operations, empty, push, and pop, and size, we're going to maintain this invariant that this representation is always pairing the list with its correct size. So the empty type, the empty type, is the empty list with the size 0, and then push and pop maintain this invariant by incrementing and decrementing size, and then our size function is just constant. Okay, so I was talking, in these grandiose fuzzy terms about abstraction and how, if we have some client code that may want to make use of this, is our change that we've now made for the sake of efficiency going to break anything? Well, let's suppose in our client code we try to inspect some data of type alpha list stack.stack, And then we pattern match on it because we're like, oh, I know you're actually representing that as a list, so I'm gonna use pattern matching because I love pattern matching, and so I'm gonna do something for the nil case and the cons case. And then you go in and you change the type, the underlying type representation to the pair of a list and a size, and suddenly your pattern matching code breaks. Okay, so this is not really abstract, and we'd like to make it more abstract. So one mechanism for doing this, which I'm told is somewhat similar to how Haskell can enable this sort of thing, is by declaring a data type locally within the structure, so that you have this constructor, capital S, stack, and then your abstract type is implemented as DT. And now the client code can't actually pattern match on this anymore because they don't have access to this locally defined stack data constructor. So that's one way to kind of make that off limits. There's another, a little bit more like module-y way of doing this, which is something called Opaque Description. It's just another way of saying, I'm sealing this, it's a way of saying that you're taking the structure list stack and sealing it at some abstract type, at some signature, capital stack, which makes it so that this type T here does not reveal its underlying representation. Yes. Yeah. Yes, that's right. So if you just use colon, it's kind of like just putting like a mask over the structure, where you're only revealing the components that are referred to by the signature. But if you just use a colon rather than a colon greater than, then the underlying representation of the types can still be visible. So if you run the code, you can see in your error messages that it's referring to things that have list shape and telling you that it has int list type or something. Whereas if you seal it like this, then it will tell you it just has type liststack.t. Yeah. Okay. So in order to get from this idea of having abstract data types to something where you can actually start sticking these pieces of code together and hope that they do the right thing, we have a mechanism in ML called functors. And functor is a terrible name. If you have a new language construct in your new programming language, don't call it functor because there are too many meanings for it. So this really has nothing to do with the definition in a functor in Haskell category theory, C++ or Prolog. For something that I'm going to talk a little bit about later, you can kind of see a connection to the category theoretic definition of functor if you're familiar with that. If you're not, don't worry. This is just a new term. Okay. So functors are just sort of functions at the level of modules. They're parameterized structures. So they're structures that take other structures as arguments in the same way that that functions are expressions that take other expressions as arguments. And in general, they have this shape where you declare a functor with some name, and you give in this case, my fun, and you take some argument here called arg. You tell it what signature you expect that argument to match. And then you can optionally give an description, in this case to the signature my sig, for the resulting structure that happens when you apply the functor. Okay, and then in your definitions, then the body of this is just the same as the body of a structure, except that you can also refer to the components of your argument module, your argument structure. Then if someone comes along and gives you a myArg matching your argument signature, then you can apply the functor and get some structor myStruct matching mysig. So let's look at a concrete example. So this is just like the first thing that I thought of when I was like, well, what's some client code that might use a stack definition? It's just a reverse Polish notation calculator. So it's just some code where you don't really care what the underlying implementation of the stack is. So you take some module stack, and then in your definition for computing with the stack, you take in some argument C, which is of type int stack.stack coming from that module. And then you use, through, again, this dot notation, the value components of the signature, which are push, and maybe you want to check the size and do some error handling or something. Okay. And then in your code, you could, if you wanted to, at the same time, have two different definitions of your RPN calculator, one of which uses list stack and one of which uses size list stack. Maybe you want to do some performance benchmarking and see which one, like how much better one performs or something like that. Okay, before I say that, yeah, okay, so you've got these two implementations of stack. You expect them to work in exactly the same way. So you should expect that this RPN calculator implementation does the same thing no matter which one of these it's applied to, right? So there's a formalization of this idea, which again came from this Reynolds 1983 paper. At least sort of the seeds of it were there. If you've heard of things like the Abstraction Theorem or relational parametricity, those came from this paper. Sort of gave a definition of that in terms of system F. And if you haven't heard of those theorems, I think they're really important and a little bit understood. So I recommend taking a look if you're the type of person who likes to look at papers. And what was a particularly useful application of those ideas was discovered by John Mitchell in 1986, which is called representation independence. And representation independence. So he was talking about this as an application of John Reynolds' ideas for data abstraction. And what that means, sort of in prose, so this is a formal theorem stated in the paper, but a summary of it in prose, which I blatantly stole from Derek Driver's homepage, is that the behavior of clients of an abstract data type must be unaffected by changes to the internal representation of that abstract data type that are preserved by its operations. Okay, so we can kind of see what this means for this example, right? We changed the underlying representation to include some extra data, but all of the operations that we were doing on this data kind of preserved some invariant, something that we were looking for in the original implementation. This is kind of saying that if there's some relationship between these two implementations, M and M prime, then any functor that makes use of M should sort of behave the same way as the same functor applied to M prime. Okay, and so all of the finicky details about what's going on here are about this notion of what it means for changes in the underlying representation to be preserved by operations, and so our examples on list stack and size list stack, should behave the same way. So somehow the changes that we made there should be considered to preserve the operations. On the other hand, what does it mean for us to make some changes to our underlying representation that doesn't preserve the operations? It turns out we sometimes actually want to do this. So I'll just go through an example of that, and we can try to you can try to work out how this generalizes maybe in your head, but. Right, so the example that I'm going to work through is this idea of having a tree traversal algorithm, which is parameterized by some data structure that is going to use as a work list, as a way of deciding which branch of the tree to work on next. And our work list signature is the same as our stack signature, except I've just changed the names of the fields to make them a little more agnostic, right? So we still have an empty, and we have a way of putting something into the work list, and we have a way of taking something out of the work list. So our stack implementation, at least if we change the names, right, should match this work list signature just fine. But so should a queue implementation. So the queue implementation here, if we just represent it again as a list, and just which looks very much like our stack implementation, except that we are sticking the element X here on the back of the list rather than on the front, and yet still taking from the front of the list, right? So this is a first, last in, first out, or whatever order rather than FIFO. Maybe the other way around. Yeah, so we've got this queue implementation which ascribes to the same signature that our stack did, yet it works in a very different way. Okay, so now we're going to write a tree traversal function that it works over this data type for trees, which should look relatively familiar. There's a leaf, you can have a node with some data and 2 branches. And then we're going to write a functor that's parameterized by some w ascribing to the work list signature. And we'll want to write a traversal function which takes a tree and then gives you a list containing all the elements in the order that it traversed the tree. So to write this function, we'll write a little helper function that takes an extra argument for the work list. And our work list is a work list of trees, of alpha trees. And the first thing we're going to do is we're going to take something out of that work list, and we've got some base cases for what to do if it's if there's nothing there, or if it's just a leaf, in which case we continue. And then the interesting case is if if we've got a node with 2 branches, T1 and T2, and some value v, then we're going to const that value v onto the recursive call where we want to add the branches to our work list, right? And we add the branches to our work list by calling the put function from the work list data structure on T1 and T2. Clear? Okay. Right, and then we start out the whole thing going by putting the initial tree onto the empty work list. All right, so then the cool thing that we get as a result of this is we can apply the traverse functor to a stack and get depth first search, or we can apply the traverse functor to a queue and get breadth first search. So this is very much an example of where we're applying a functor to 2 different things, and we're getting a very different behavior. And this is somehow correlated to the change in behavior that you can see from a stack to a queue. But it's it's a case where this representation independence thing doesn't really apply. So yeah, so this is just a sort of a flavor of what you might want to use functors for. Right, so I'm going to quickly go through a couple of other examples because I'm sure lots of you, especially the Haskellers in the room, are probably thinking that some of these ideas look kind of familiar. So one common use case for functors is to kind of get something like type classes, where we can parameterize a module by some values that implement like common operations like comparison and equality. One of the most common examples is if you have some type T which has equality and less than that you can implement on it, and you call that ord, and then you can parameterize a set data structure by that ord type for its elements. So then the set type will expose these operations for empty and add and so on, and you can implement that as a functor ord set, which takes an element elem implementing ord, and then then implement our element type as elem.t. And I'm showing this mainly just to illustrate, because the previous examples didn't illustrate when you might want to apply a signature to the result of a functor, so this is one of the common cases for doing that. And then finally, I'm going to pause for questions in just a little bit, but so finally another example that comes from a project that I've actually worked on is kind of is called Functioning, which is a little game framework, and it's kind of using this idea that a functor can be used as a framework in some sense. So you've got some library functions that provide graphics and physics, and then the game implementer says, okay, here's how my game updates its internal state, here's how it handles events, and here's how it renders. And then you throw that into the functor, and it gives you the main function, which you can call, but that does all of the kind of low-level implementation of the game loop. And so just at a glance, like this is kind of the core of the implementation of the functioning functor, where we're using some game that implements our game signature and using it to put all the pieces together into a running game. Okay, so far we've covered how signatures and structures and functors work in standard ML, and talked about how signatures and structures relate through matching, and how functors, one of the things that functors support is this kind of idea of working on two things separately and then putting them together later. So separate modular development is kind of the buzzword for that, and how representation independence is a key idea for doing that. So I'm going to move on and talk about the type theory, a little bit of the type theory underlying this, but I just want to pause here and see if there are any questions about what I've talked about so far. Yeah. Yeah, so with objects, I mean, so there are certain uses of objects that are very similar, particularly if you use something like Java interfaces, where all you're doing is specifying the types. But in general, there's nothing like classes where you give types and implementation at the same time. It kind of separates the idea of the type specification and its implementation. Another difference is that this is again the sort of relationship between signatures and their implementations, which is that it's all entirely structural. So there's no going in and like declaring, okay, this set, like, or this. What's a good example? Like there's no just declaring that something extends another class or is an implementation. I mean, you can declare a description. You can give a description for structures in terms of what signature you expect it to match, but that's really just a check. That's not anything that will cause a relationship to occur in the type system, if that makes sense. This is the difference sort of between nominal and structural subtyping, if those words are familiar to you. No, there is subtyping, but it's entirely structural. It's entirely inferred by, like, does the structure match the signature? As opposed to if you're saying, if you use inheritance or something in OO and you try to say extends, like, you're establishing a relationship but just by saying that, rather than asking the type checker to check it for you. Yeah. Yes. Mm-hmm. That's right. Yeah. Yeah, so it's possible. So if you can have a functor from that takes two things that implement ord and then gives you another ord, which is on the basis of like the ordering between the components of the pair, things like that. For a lot of those use cases, you want something that's a little bit different from what standard ML gives you. That's going to be a little bit easier to explain once I do the next part of the talk. So just as a preview, which probably won't mean anything, it's the difference between applicative and generative functors. And I'm like about to tell you what that means. But yeah, so it's possible to do this, but not really in ML, in SML, sorry. Yes. Yeah, so I mean, the kind of the core idea here that's going on with functors is, again, this idea of separate modular development, of being able to say, I don't know what my dependencies are right now, and I don't want to do everything in dependency order. I want to work independently of those implementations and do this other thing. And like type classes can buy you some of this to some extent. One of the major differences there being that a type class sort of expects there to be one canonical implementation for any given type, any given underlying representation type, and this allows you to have multiple, multiple ways of even providing the same concrete type, but giving multiple implementations for that. So, yeah. Okay, so I will move on now. So I'm going to talk a little bit about the type theory, and it's not too scary, right? So what underlies all of the languages that are sort of in the program for this conference is this thing called System F, which is kind of just a lambda calculus with this idea of using the for all quantifier from logic to quantify over types. So this is what gets us what you're familiar with as like parametric polymorphism. And all that is really going on in some sense with this notion of type abstraction is using the existential quantifier from logic. So you have some term E that you can type as there exists a type T such that tau. Then this is some implementation of a module that can be given the signature with abstract types T. So to look at that a little bit more up close, for example, these ideas were first written about, I think, in this paper, Abstract Types of Existential Type by Mitchell and Plotkin. And one of their core examples in the paper is actually a stack, and I did the stack example before looking that up, so that was cool. So you can kind of see, so this is the logical structure here, where it's using for all exists and the logical notation for and or and like the unit type. And so this is sort of saying you can represent the stack type as something that parametrically quantifies over its element types, and then existentially quantifies over this stack type S, and then gives you something, and then gives you an S for yes, yeah. Oh, so it's sort of like I mean, have you seen like lambda notation where there's like a dot after the variable and okay, so it's just all the dot means is it's just kind of like introducing a new scope, right? So you're saying, for all t, you can kind of ignore it. It's just sort of saying this is the end of the variables we're declaring, and then here's the rest. Okay, yeah. So we're quantifying over some element type t, and we're saying there exists some stack type S such that there's an empty of type S, and there's a way of taking an element type and an S and getting an S, that's push. And there's a way of taking an S and getting either some element and an S or nothing, and that sort of corresponds to this pop here. So that's how the programming notation and the logic notation line up. So this is a paper with a funny name, and it's also great because it sort of says like all of the stuff that we did for the couple of decades after kind of after Reynolds and Mitchell and Plotkin did all of this formalism. After we started building these languages, we started trying to account for them with more and more complicated type theories, and people got the impression that modules were really heavyweight. And then Andreas Rothberg and Claudio Russo and Derek Dreyer wrote this paper that was like, actually, we can interpret all of this stuff directly as system F, as just this for all and exists quantification over types. So that sort of goes through and really, explicates this idea that all that we're really doing is, can be accounted for logically. One of the a little bit weird consequences, so there's a little bit of a consequence here when you're just trying to account for these things using the existential quantifier from logic. And so this is this idea where you have some functor f, it takes an argument x, signature a, and it opaquely ascribes to some signature exposing a type t, maybe some other stuff, right? Okay, and then you're given some module m, which implements that signature, and you want to ask this question: does f of m dot t is that type, that abstract type, the same as f of m dot t? And this is not a typo. The two sides are the same, right? So we should kind of expect like equality to be reflexive, and that this might be the case, but in fact it's not. So. So in more concrete terms, one of the reasons that you might kind of like this to be the case is like you have some two different instantiations of ordered set on like the int-ord structure, and you ascribe both of these things to set, and then you try to add something to, you try to use S1's add function on S2's empty value. And in the straightforward account, kind of given in terms of system F, for abstract types as existential quantification, this does not type check. And this is also the choice made by standard ML, and this is what's known as generative functors. It's kind of this idea that every time you apply a functor to something, it's generating a new type for the abstract type. The dot t that you're referring to is going to be different every time you apply the functor. On the other hand, in OCaml, if you do this, then this will actually type check. So it has this idea of applicative functors that if m if m and n are the same two modules, then f of m should be the same as f of n. So you might think that this is all, this is like, okay, down with logic, like it doesn't work, okay. Right, okay, so when might you actually want generativity? So interestingly, ML is a language with state and with effects. So one of the situations, and perhaps arguably all of the situations where you want generativity, involves some notion of state. So if you implement this ORD signature with something where the underlying type is int, you have int.eq, and then for less you flip a coin, and if heads then you do int.less, and tails then you do int.greater. Okay, now every time you apply set to this functor, applied to the empty module, then you might get some different implementation of this less function. And now, these two sets are not actually compatible. So you don't want to try to add something from one set using one set's add function to the empty set or to any other set built up by the operation in the other implementation. So in general, this idea of applicative versus generative functors, like when you want to use one practically in your code versus using another, corresponds to pure versus impure code. And I'm saying this kind of as a summary of what Derek Dreyer has decided after years and years of studying modules. And this might kind of suggest that we would like to be able to account for both. And effing modules figures out a way to do this, although it's actually interesting that the accounting for the semantics of this applicative notion of functor, well, you can do it in sort of an extension of system F called F omega. It's not quite as simple as the story for generative functors. So that's just sort of a brief rundown of like what's going on with this whole discussion on generative and applicative functors, if you've heard about it. So now here's just like now that we're talking about some functor types, there are a couple of implementations of ML. There's standard ML, OCaml, Moscow ML, just to name a few. So I just want to talk about like what kind of functors these things have. So in standard ML, we have generative functors. In OCaml, they used to only have applicative functors, and I think they recently added generative functors. Moscow ML was this experiment where they were like, we want to have higher order functors, like we want to have functors that can take functors as arguments. So that totally should make sense. And then they were like, but we also want to have generative and applicative functors. And then there was this email across the types thread that was like, oh, if you try to intermix generative and applicative functors through this higher order functor system, you get unsoundness, and like maybe here's some ways that you could do this, but Moscow ML system doesn't do it right. So things get complicated, right? Okay, but so beyond the implementation of all of these MLs, there's been some research on how to talk about modules as first-class values. So not just making the module language part of the expression language. Having recursively defined modules, and something called mix-in modules, which are like sort of an alternative to functors, where you can declare some things concrete and some things abstract that are waiting to be filled in later. And so what you can do with all of these mechanisms include things like interpreting what happens in object-oriented languages and type classes. And so the work sort of below the line break is meant to sort of be like, here are some applications of some of these newfangled module ideas. And one of the more recent ones is a package management system for Haskell called Backpack, which uses this idea of recursive mix-in modules. So that's pretty much all I have to tell you. Just to summarize, so modularity is a pretty fuzzy term, but we actually have theorems about it, which is pretty cool. We don't have to talk about it like it's just this subjective thing. And really, it's a tool for humans. It's about reducing your cognitive load while you're programming, so that you don't have to think about what all the other code is that you're working against, which may be written by other people or whatever. And this can be enforced by type structure. This is like fundamentally an application of type systems. And the John Reynolds paper goes on about this for a while if you're curious about the justification for that statement. So alternatively, give the ML module systems a try. Open up OCaml or SML and just see what you think. I'm not here to make judgments for you. I'm just trying to tell you about what's out there. So give it a try. If this sort of type theory stuff interests you, then these are all really, really classic papers, these 3 that I've listed. And then Derek Dreyer and a lot of his collaborators sort of have carried forward that work into the modern age, and it's definitely worth checking all that stuff out if you're curious about the state of the art. All of the code for this talk is up on GitHub, and please feel free to talk to me on Twitter as well. So, thank you.